were exactly twice as many moles of HCl, it would be neutral. And it actually comes out to just less than twice as many moles of HCl, which means that the resulting solution is going to be basic. There's not quite enough HCl to neutralize all that magnesium hydroxide because of the 2-to-1 ratio. So when you're looking at those neutralizations or titrations, which came up again in the written part at the end, got to keep in mind the equation. Is it reacting 1-to-1 or 2-to-1 or sometimes 3-to-1 or 3-to-2? Acids and bases can react in various different ratios. You've got to balance the equation to find out. All right, chromium is +6 for the oxidation state in potassium dichromate, or sorry, potassium chromate. And for an ideal gas to triple in value, for the volume to triple in value, one thing that can be helpful is thinking about what types of things cause the volume to increase. Certainly, decrease in pressure, or an increase in temperature, or an increase in moles. And the only one that makes sense here then is D. If you decrease the pressure by a factor of 3 while temperature stays constant, then the volume has to triple. Phosphorus has 3 unpaired electrons in its 3 p orbitals. And this looks maybe hard to tell, but this should be a gas evolution reaction because you have acetic acid, which is that first molecule, and potassium carbonate. We know carbonates, when mixed with acid, tend to form carbon dioxide gas. All right, and then this one's a pretty straightforward limiting reactant problem. You've got to calculate moles of N2O4 and N2H4, and then figure out which one is limiting, and calculate the yield of nitrogen based on the limiting reactant. Okay, more questions about any of those? All right, let's take a look at the free response ones. So this one went sort of okay. One thing that helped people here, I think kind of by accident, was you really were supposed to check for a limiting reactant because you're given 2 quantities of reactants and it doesn't tell you which one is limiting and which one's in excess. So you really have to calculate moles for each of those before you come up with a theoretical yield. Now, in this particular problem, the limiting reactant ends up being the potassium peroxide, which is the first one listed in grams. So a lot of people just kind of took that and ran with it and didn't check for limiting reactants. Couldn't really take credit off if you still got the answer right. So you know, you got it right. But watch that. Whenever you're given 2 quantities of reactants, you got to look at both of them and figure out which one is limiting. The answer for this one ended up being, somebody got it right? 27.1171. 27.117.
15.19 grams.
Okay, but there's only 3 significant figures, right? So yeah, 27.1 grams for the theoretical yield. And then this one didn't ask for percent yield, just the theoretical. Oh no, it said percent yield too. So the percent yield is going to be 21.8 divided by that theoretical yield, 27.1. It comes out to about 80%, yeah. Okay, if you want to see that, or if you want me to look through like what you did, if you're not sure how that problem works, come see me sometime so we can go through it. All right, electron configurations for the following atoms. Almost everybody got the first one right. The second one, don't forget that copper is an exception because of that full D shell that it can have. So it's going to be 4s1 3d10, not 4s2 3d9. The lead one, a lot of people got most of it, that it was that you start with xenon and you end with 6p2 because it's the second one in the p block. But where most people messed up is that you have to actually fill the F, the 4F, as well as the 5D. That's the lanthanides going through by 57 to 71. So don't forget the Fs when you're doing those heavy element electron configurations. Okay, so this was a big one. we react methane gas with water vapor, produce hydrogen gas and carbon monoxide. Several people wrote carbon dioxide, so be careful with that. Just read things. I know you know the difference between the two. I just think maybe you didn't read it or weren't thinking quite right. Then when you balance this one, it should be pretty easy to balance. You just put a 3 in front of the hydrogen. Okay. So in this one, you definitely have to check for limiting reactants. The methane gas was 25.5 liters at 732 torr and 25 degrees C. The water vapor was 22.8 liters at 702 torr and 125 degrees C. And then the amount of hydrogen produced was 26.2 liters at STP. And that's the actual yield. So we want to find the theoretical yield of hydrogen in liters or in moles or whatever, and then get the percent yield by dividing them. So generally when we make a percent yield, that's got to be either moles or grams. Moles and grams should give you the same number. With gases, I believe liters will also give you the same number because they're proportional. So whether you solve that however you did, it should be fine. So all you got to do is calculate the moles of methane gas and water vapor, and then calculate the theoretical yield. So what were the moles of, anybody have that handy? What was the moles of methane? And what, 1 point? Okay, so we'll say 1.00 moles. And what about water? Okay, so clearly water is limiting since they're supposed to be 1-to-1. So you use the water, you take 3 times 0.645 to get the total moles of hydrogen. You get 1.94, and that's the theoretical yield. So you can either then take this number and convert it to moles by dividing by 22.4, and then just divide by 1.94 to get your theoretical yield, or you can take 1.94 and convert it to liters and then divide however you did that. But it should have come out to something like 60-ish%. Is that about right? Okay. All right, the observation. Some of you did a great job with this. Some people not so much. So let's talk about this. Explain the observation using concepts from the kinetic molecular theory. So that means we want to know, we don't want to just restate what happens. We want to know what is it about the molecular motion, the motion of the actual molecules in that balloon is causing the change when it's doused with liquid nitrogen. So dousing a balloon with liquid nitrogen means that you are cooling the gas inside the balloon. So that's why it says collapses and not deflates. The gas doesn't leave the balloon. It's not effusing from the balloon or something. It's simply getting cooled by the liquid nitrogen. So what happens when you cool a gas? Well, what I was looking for here was that you said something about when gas molecules, when the temperature drops, that means that their average kinetic energy has to go down. If their average kinetic energy goes down, that means that they are moving more slowly. And then that's basically what I was looking for. And then something about how that connects to the other stuff. Balloons are a little tricky because they are technically a constant pressure situation. Or we often think of them as a constant pressure situation. So that when a balloon is collapsing, it is the volume that's changing at constant pressure. Now in reality, the inside of a balloon is at a slightly higher pressure than the atmospheric pressure because it's kind of push, you have to like push air in to blow it out, but because of the resistance of the rubber. But you could think about that either way. So however you talked about that with regard to pressure and volume, I was okay with. The best answer, I think, is to say that the volume decreases because the system has to stay at constant pressure. And if you have slower gas molecules and you want the same rate of collisions with the walls, then you need a smaller volume. And so the volume collapses to accommodate that. If you talked about it with pressure instead, that was fine. But a balloon is really, really the change that's being described here is not a pressure change so much as a volume change. All right, questions about that one? So a couple of common wrong things I saw there. One was simply stating gas laws. That's not the theory, that's the law. So simply saying, well, when gas gets cooled, it lowers its volume. That's true, you're right, you're correct, but that's not explaining using kinetic molecular theory. And then there were other things where just people said stuff that was wrong, like that, you know, I don't know, that the liquid nitrogen, the force of the liquid nitrogen being poured on it causes the balloon to collapse or something like that. That's not really what's going on here. All right, balanced equations. And what are they? Iron metal and sulfur make iron 2 sulfide. Okay, that's the balanced equation. You're reacting two solids to form another solid. In this case, the best description of it is redox, because you have two zero oxidation state elements combining to become a +2 and -2 oxidation state. So that's the best description here. It's not really a precipitate reaction in this case. This one is a precipitation reaction, so Ki is mixing with lead 2 nitrate to make lead 2 iodide precipitate. That is best described as a precipitation reaction. It is not a redox reaction. Nothing is changing oxidation state here. And then sodium carbonate reacts with nitric acid. So you got a carbonate reacting with an acid. That's going to be a gas evolution reaction. So that one's best described as a gas evolution reaction. You can also call it an acid-base reaction if you want, because it is an acid acting with a base. That's fine. It is not a redox reaction, so you should not have put that this was redox. Nothing is changing oxidation state. Like a lot of people said carbon was changing oxidation state here. It is not. It is staying at a +4 oxidation state throughout this reaction. All right, and then another problem, this time in moles instead of grams. We've got iron 2 sulfide reacting with hydrochloric acid, and you didn't need to know the states here, to form iron 2 chloride and hydrogen sulfide. If the initial reaction mixture contains 0.222 moles of this and 0.650 moles of this, how much of the excess reactant remains? So be a little bit careful here. Some people just simply subtracted 0.65 by subtract 0.222. That doesn't work because it's not a 1-to-1 ratio. So you need twice as many moles of HCl. So you need, obviously the iron 2 sulfide is limiting. You need 0.444 moles of the HCl to react with 0.222 moles of the iron sulfide. So the excess reactant left is 0.650 moles minus 0.444 moles. That's going to give you the excess reactant left. All right, this one was a little bit tricky only in that it came toward the end of the exam, but it's kind of an easier question. Not limiting reactant problem. Both of those quantities are stoichiometric, so you actually can just add them together to get the yield, but you didn't know that until you actually do the calculation. So you have to write the equation, figure out that there is no limiting reactant, And then you can calculate the theoretical yield of PCl3, which is just those two masses added together. You can divide for the second part, 18.34, divided by that gives you the percent yield. In B, yeah. All right, and then finally a titration question. So again, a lot of you did most of the calculations reasonably okay here, but forgot to look at the actual chemical equation. In your titrations, when you're doing a titration between HCl and NaOH, it's a 1-to-1 molar ratio. So you just use the direct number that you get from the moles of NaOH and you calculate your moles of HCl. But in this case, that's not what was happening. This is sulfuric acid. So we have to look at the reaction, which is sulfuric acid and sodium hydroxide. And that reaction is 2-to-1. So however many moles of sodium hydroxide you came up with in the 3 trials of the titration, which was all right around 0.01 moles, I think, or maybe 0.001 mole, 0.001 mole, no, 0.01 moles or 0.009, something around that range. You had to cut that number in half to get the moles of sulfuric acid, because it's a 1-to-2 ratio between sulfuric acid and the sodium hydroxide. So the ultimate concentration ends up being something around 0.005 or something, 0.05 molar, something like that. Is that right? Somebody got it right? Yeah. So if you didn't get that ratio, then you got the final concentration to be more like 0.0 or 0.1 molar. All right. Questions about the exam? Okay. So one thing to keep in mind with this exam, because of the kind of change in what we're doing and how we're talking about Lewis structures and drawing things and shapes and quantum whatever, that means that we're not going to do a lot of these types of stoichiometry problems again, or gas law problems, until the final. So tuck it away, but don't forget about it, because they will come back, but we aren't going to mess with them for a little bit. So if you had trouble with a lot of these types of calculations and these types of problems, please keep working on it. We've only got a couple weeks left. You got to catch up on that stuff while also keeping up with the new stuff so that you can do great on the third exam and the final. Also, another thing I noticed on this exam, most of you are pretty good with the naming at this point, which is great, but I was still seeing some errors that messed you up, like saying that nitrate was -2, or messing up what bicarbonate is, or not knowing acid formulas of sulfuric acid or nitric acid. So keep going back and reviewing those, because those will keep being important as well. All right, all good? Okay, let's take a break, get some lunch, and then we will talk about Lewis structures. Yes?
So the one that was saying identified in the third period would end up being aluminum based on the
ionization energy.
So the ionization energy going from 1 to 2, it was more than 3 times. Then it was a normal ratio, or then it was like less than double, and then it was like 3.5 times. It was 4. So like greater than 3 times, not greater than 4. So I chose sodium first because that was a huge jump back compared to the next one. But,
Okay.
So, I understand. They're both large jumps, and that's why I got confused. Is there?
Yeah, I can do that. So, like, yeah, the way I would think about that is, if we pull up that chart of all of them. I think you can think about the absolute values rather than the relative values. So you were talking. So you would expect that because you're always removing one electron, if everything was always the same, you would expect a linear increase in energy. So you would expect, like 1,000 kilojoules more, 1,000 kilojoules more, 1,000 kilojoules more. that would be a linear one.
Yeah.
What you're talking about is an exponential. So you're saying you would have expected it to double or to go 3 times and then 3 times and then 3 times or whatever. So you see what I'm saying?
Yeah.
So like when you look at these, if you look at like the difference between sodium and aluminum, you said, well, this is like a little more than triple.
Yeah.
It's about triple. And then
This
it's
is 4 times. So,
4 times from this one.
Well, this is a 4 times jump from here to here.
Oh, from here to here. Okay.
Yeah. So that was my thought process.
So that was your thought process.
So
then
I identified that this was a huge gap. Like this was just over. This is right on triple, and then this was not even twice. as
right.
much.
So that's what I'm
why
saying. That's
I
the problem.
identified-
So don't think about it as relatively how much bigger it's going up. Think about the actual value. Say like, okay, this one's about 1,300 more than this one.
Sure.
And then this one's about
Okay.
900 more than this one. And then this one is about
Okay.
8,000 more than
Okay.
this one. So the actual value
Okay.
of the difference is what the big jump is,
Okay.
rather than thinking about like double, triple, whatever. So
Okay.
think about the actual like the
Got
the
it.
amount of increase.
Okay.
Because as you see, even like with these big ones, the number gets quite big over here. Like these numbers are as big as these numbers, but you can see that the increment is about the same or somewhat the same each time before the big jump.
Okay.
So yeah, it's the increment, not the ratio, I guess
Okay.
is the way to say that. Yeah.
Okay. All right. That was the only thing. That was what I.
Yeah.
That's why I got that wrong the first time. I was like, okay, I can see. Like when
Yeah,
I looked
that
at it, I'm
makes
like,
sense.
okay, like I see there's huge jumps. It was to me.
Right.
Look at the ratios. It looked like it was a 50-50, and then it was just like
Yeah,
I guess wrong.
I can see
Okay,
that.
So it's just
So think about the
actual
value or the increment, not the ratio.
Is there any chance you're willing to give us grace points if we put boron instead of selenium because we learned
No,
that the
it's
trend
not
was up
right.
and towards fluorine and not about the.
I know, we didn't actually learn about that part, so that was
I
upsetting.
got 95 because that was the only one I got wrong on the first try. I
If I
got it
would've
right on the
gotten that, I
second
would've
try,
gotten
so if
90.
I got it right on the first try, I would have got on the try.
So that's a good, but I think that's a good lesson. Is you can't. This isn't, it's not biology. It's not just saying like.
It's not lessons on quizzes.
Sure, but well, no, quizzes are meant to be a measure of where you're at the time before the exam.
So to be fair, we did discuss that we would rather him challenge us on quizzes and homework versus on tests.
Chris, stop.
I'm just
But-
saying.
I thought we
No,
agreed
but the
on
idea,
homework,
but
not
the idea
quizzes
is
and
that you have to use all of your thought and all of your knowledge to try to solve these questions. It's not meant to be like, oh, this question is asking about this specific rule, therefore I will apply this exact rule and solve the problem.
I like that stuff. That's like the biology, anatomy.
Yeah, that's easy stuff. That's stuff,
It's not easy.
But this is
For
college.
anatomy,
You have to like.
memorize like 400 words a week.
Right, the quantity is difficult, but it doesn't require.
The highest one?
It requires a lot of memory,
Yeah, which I
but you
thought
don't
were
have to like
totally
figure it
spaced.
out. It's a different way of thinking about something.
Like I understand you have to use like one word to get from boron to fluorine, but also.
All right. Oh, I should grab my
selenium's
plug.
too lower. Boron's in the same row.
I don't think a 95 is gonna hurt you.
I mean, I don't think it's gonna hurt me, but that's like really unsettling that that was the only one I got wrong and then I got it right on the second try.
How'd you do on
And it was
test?
question 9. I was so
I got an 88. How'd you do?
81.
I just want this class to be done. These next 2 weeks are gonna
We're
be
so
so
close.
hard.
I feel like this next part is much easier than.
Right,
the
but then we
last.
have to like full gear do everything that we've learned to prepare for the final, because everyone's gonna want to do really well in the final to replace an exam grade.
Does the final exam, can we have that one not count?
No, that one's gonna count no
That
matter
one
what.
always counts, and if you get a higher grade on the final than you did on one of
They
your
can also count for one?
Yeah,
it's
so
not
if you
like
get lower, it's going in, but if you get higher, then it's going in twice, basically.
That's kind of weird.
Yeah, so if you
I
got
mean-
like 85s on all of them, but then a 60 on the final, the 60's going in. But if you get 85s on all of them and then an 89 on the final, one of the 85s will also be an 89.
It should just be like another test where like, if you get a better grade, then you can replace some of your tests, but if you get a lower grade,
You could drop it.
I think the final just counts for too much, so he can't be like, it's a cumulative versus a
Yeah, cause then if I did well enough on the first 3, I just wouldn't show up for the
That's what I was
final,
gonna
and I
say,
don't
like-
think that's what they want.
Yeah.
Cause like so far I have a good test average, so if that continued into the 3rd one, I just wouldn't come to the final.
I mean, they need to use it to compare to, because it's a standardized test, they get to compare it, they get to compare teachers as well as they get to compare schools and see what they're deficient in. So like, they need that data.
It's more data for you, not grade anyway.
I could not show up to the 3rd one and hope I do well on the final and
That's
have
true.
it go in as
You
the
could
3rd and
totally
4th.
skip a test.
Like I could just not go to the 3rd one and then hope I get like a 90
Yeah.
on the final and have 2 90s go in and not go through the work of taking the third exam. But I don't think I would ever
I'm
be
not
able to do that.
Yeah, I'm not taking that risk.
Because what if I do way better on the 3rd exam, then I can replace one of my earlier test scores.
I'm excited this one's just conceptual versus figure out which formula you want to use. Okay, now
And
compare
then
these
do a lot
constants.
of
Now
math,
do yeah.
and think about everything really deeply and then do more math.
Yeah, and then punch one thing wrong in your calculator and oh
And then you're
whoops.
screwed. Oh, I just got really cold. The air
You
started
know, I'm always
blowing.
freezing.
Oh,
It's
yeah, I
less-
forgot.
Are you?
I'm an
always
oven.
warm?
I'm an oven.
I'm always cold. So
So when we were doing the one lab where it's like you have to see which one produced gas, which one created heat, I couldn't tell which one was heating up. I had to use the
Oh,
to figure it
yeah.
out.
Yeah. What?
When we were doing the chemical reactions and it was like, which one of these is
Feel
heating up?
warm.
I'm like, I don't
Oh my
know.
god, yeah.
I don't know.
You guys both ran over and were like, tell me which one's
it's
hot.
90 degrees and when Jesus switch it, like it's so
What?
sad.
This
Like what?
Oh, this room is great. Ugh.
That's just
But the
not-
airflow.
I know, it's so annoying. They shake and I'm like, okay.
There's no way he's gonna make us get to memorize that. There's no way. Well, just remember we have to know all the elements by the exam.
No.
Well, he's still
We
gonna.
need to know like the.
Well,
He gives us the periodic.
Which is
but
not
he doesn't
many.
give us the names.
Oh.
I mean, like,
It's just that that's not like.
You can
the
kind of,
memoir.
you can kind of guess with the.
Yeah. Yeah, it's just like another extra thing that's just.
Yeah.
I mean, he's not gonna ask us ones. Like, the worst one he's gonna ask us is like antimony, which is what he's been using, which is SB.
Which one?
Antimony?
It's SB. No,
I mean-
no, it's.
The ones that
Those
just
weird
makes my
letters
work.
are hard, like.
Yeah, all the ones that are using,
Silver.
yeah, all the ones that are using their Latin root
I
are,
always mix up lead and silver. Silver's AG, right?
Yep.
Okay.
What's left?
PB.
Iron.
Mercury is HG, gold is AU.
Silver is copper. Or like gold is like AU, come back among gold. I remember that from like 7th grade.
But yeah, it's not like he's gonna ask us what he is a beryllium or something stupid like. I mean, I guess he could ask us like radon, which is RA, and stuff like that. Like francium, cesium, rubidium, potassium, sodium, lithium, hydrogen,
No, yeah, once it gets above 8.
beryllium, magnesium, calcium, strontium,
Oh, I
barium.
do.
I watch Zumba.
I'd much rather be cold than hot.
I'm watching Zumba now.
They care more about like what you know how to do.
I know, I know.
They try and take points.
Yeah, no,
Nailed it.
no
I wanna
all
go
your
on
alkaline
so
metals,
badly.
alkynes, and alkaline metals, no
I can make
your
some
noble
sense.
gases, and your halogens, your noble gases, and the few transitions over the acids. What?
Other than that, I love
I just ran out of time. I didn't finish the titration,
I feel like no one gave you
and then I
put 4 at 15 instead of 14, and I'm like, at one point,
I did that, and then I didn't finish this because I started looking at the time, and I'm like, I know there's still a couple steps in this. I'm gonna go and move on to the next one, so I know I just finished this question.
I go on when you come.
So
It's
3:02. Like, he announced like with 2 minutes left, and then anyway. I also the final is 2 hours, right? 2 hours
Yeah, but they're all.
I think so. I have to confirm that time. I feel like it's a weird time. Like it's not exactly 2 hours. It's like 110 minutes or 130 minutes, like something like that.
I was talking to someone in my class who took this class last semester.
Okay.
And they were saying that the hardest part about it was the time. The amount of
Yeah,
time.
it's just faster.
Yes.
Right. Yeah. The final is the very last day of class, so a week from tomorrow, or 2 weeks from tomorrow.
These are 6-week or 8-week long classes?
8.
Really?
I mean, it's been going pretty fast though. It's not like it's like slow. So I don't mind it. I just, I don't get how like people, I mean, if your grade's really bad, how people can drop at 5. Oh yeah, so you're almost got confused.
Yeah, but you, by that point, I mean, you're probably not going to pull it out from there, from that point. Although it's happened,
You know, you went through all that.
So when I was in high school, there was a policy that you could fail both semesters as long as you had a B or better on the finals, you passed the class. Used that a lot. That was great. I was real lazy in high school.
Yeah, that's a big difference with high school and college. I also had that experience where you could pretty much just, like be there and take exams and be fine in high school, and then that doesn't really work in college anymore.
Not as much.
Depending on the
you
class.
could choose to not show up.
Well, right, but
It's a lot harder.
it's, yeah.
Also, in like high school, you like had turns on or like that was so bad grades basically.
Yeah. I didn't, that's why I didn't pass the final. I was a really bad student in high school. But now,
I was a good
older,
student.
wiser.
I was a good student in high school, but I didn't try hard. I was like a lazy student, but I got good grades. And then I got to college and it was like, oh, I'm gonna fail everything if I don't actually do the work.
Oh,
So
I got straight A's, all A's but 1. I got B one semester, and it was way more work than it was worth. No one didn't matter. And I was like, well, this is stupid. It's way easier just to do nothing, pass the final, which is a very bad lesson they taught me. But
Yeah.
They probably did that to boost their graduation rate.
I mean, the reality is most people, that's not enough.
Do you know the averages of the exams, like in order, like which one's highest? No, that's like a
yes, usually, so for sure the second one is always lowest. Not for every person. A lot of people actually improve significantly on this second exam, but generally the second one is lowest. The third one is weird because it comes after the withdrawal deadline. So the average is usually higher, but it's also because a lot of people who wouldn't have done well have dropped by then. But yeah, the third exam can kind of go either way, because there's not the mathy limiting reactant stuff, which sometimes brings people way down, but there is all this new brand new stuff, hybridization, molecular orbitals, things that nobody's really seen before. So sometimes that causes problems too.
Are we so? So you said that the finals could, if you do good in the finals, replace from those tests.
Yes.
How often does that happen? If that makes any sense.
Almost everybody.
Okay.
What if we just really found that oxygen just
Then I wouldn't replace anything with it.
You
But
still
like it's,
protect-
I don't think you were here. I was talking to a couple of you the other day. The final is a very good measurement tool. It's year after year, we look at it, we evaluate it, and it really does a good job of showing you where you're at. So most people, with few exceptions, tend to get on the final about the same as what they've gotten on all the exams. If they've been pretty steady. If they've been like this, then who knows? But if you've been pretty steady on the exams, you're going to pretty much get the same exam on the final. It's because it's a scaled score, so it is curved based on national statistics. So your actual raw score could be whatever, but when it's scaled, it ends up being pretty much like what you would expect. There's not most people do better. So most people do better on the final than they did on their worst exam, and so it ends up being kind of in the middle. Like they end up doing on the final in between their best exam and their worst exam, kind of. Some people have a terrible day and tank the final. Some people get super lucky and
Guess really well.
guess really well and it goes fine. Like I've seen all of that stuff happen, but I would say the vast majority of everybody scores about as you would expect in the final. Yeah.
Finals only multiple choice, right?
The final's all multiple choice. Yeah.
You also correct for concepts that we didn't
Right.
learn.
So there's usually like 3 or 4 questions from like the heat stuff or from yeah, it's usually pretty much just the heat stuff that we end up throwing out.
But if we happen to guess correctly.
But if you happen to guess correctly, it still counts for you. Yes. So you still they don't get we don't like zero in on those questions and just strike them out. The whole score gets scaled in to account for that. So if you get them right, they still help you anyway. So if you want to go study up on some chapter 6, you could probably get yourself some extra points on there. All right, let's continue.
Credit on the final is what you're saying.
Yeah, I guess technically there is.
There you go. You
Um,
got extra credit on the test.
All right, so yesterday we started writing Lewis structures. Oh, let me start the streaming here. Okay, so we talked about how to draw Lewis structures like this. The last thing we did, we kind of ran out of time, so this Lewis structure isn't totally complete. The structure itself has to account for the charge, the overall charge of the ion. So in this case, we need to put that this still has an overall -1 charge to make sure that it's correct. We also talked about evaluating Lewis structures. We're going to get into that a little bit more now. So there are a few different ways that you could draw this structure correctly, and of course lots of ways that you could draw it wrong. But one of the different ways that you could draw it correctly is, maybe you did, because we all tried this one. Some people may have drawn it like this, or like this, with, as long as you did the correct things with it, like that. Okay, those are also correct structures. Now, are they the same or are they different?
The same. I mean, in the 3-dimensional figure, like, just perception. Right, so these exist on 3 dimensions.
So it's a little tricky. It kind of depends on your definitions. They're definitely equivalent, right? Like, if you had, let's say you actually had 2 of those molecules, you could twist one and make it just like the other ones. Agree with that? Jessica?
Sorry to cut you off.
No, it's
So
fine.
are they like, well, can you say they're different because like, don't the double bonds have more of like a weight to them, like they've been further, or they've been in a different angle?
Yeah, so if we were to actually like zoom in on these molecules, let's say you have these 3, they are different because the double bond is shorter, and we'll talk about bond lengths in a little bit, but the double bond is a little shorter than a single bond. So you would expect to see a slight difference from where that double bond is, but again, you could rotate them and they would be the same as each other, because you could have the one that has the double bond down here or the one that has it over here. And there's actually a word for this. These are different ways of arranging the electrons to still give you a correct Lewis structure, and these are called resonance forms. And they're usually drawn with double-headed arrows, double-headed, double-sided arrows between them. That word resonance means to oscillate, and that's kind of wrong. But the original theory of this, they thought that what was happening was that double bond was basically flipping around. like it was oscillating from one form to the other and back again and kind of like flipping back and forth at really high speed. Now we actually have tools that can measure that, and we know that that's not really happening. What's really happening is that the actual structure is a hybrid of the resonance forms. So if you actually zoom in on a single nitrate ion and you measure its bonds, you don't see one double bond and two single bonds. You see three equivalent bonds that are in between, that are about 1.3, 1 1/3 bonds. So the actual hybrid is really hard to draw because of that, because it doesn't account for these electrons, and that's one of the limitations of this Lewis model, is it's a localized electron model, which means that we're assuming that electrons are localized on specific atoms. And in reality, that's not quite right. So when we start thinking about these ideas, it kind of breaks down a little bit. But a resonance hybrid might be something like this, where you have like partial bonds that you could describe as a 1 1/3 bond between a single bond and a double bond. So when we're actually drawing these structures and using Lewis structures and using Lewis theory, we usually don't draw the hybrids because it's like, okay, where do you put the electrons? How do you account for the octet rule if you've got these weird partial bonds? We usually just draw the regular structures, and then if we want to express resonance, we draw the different resonance forms that it could have. So for something like this, that resonance is, it's interesting, but it's just kind of like, okay, it's there, they're all the same, it doesn't really matter. But in other structures, it can really make a big difference. So for instance, we'll look at this in a little bit, but thiocyanate ion is SCN. And there are a few different ways you can draw a Lewis structure for SCN. Here's one. These are different resonance forms. Another one. And then here's a third one. Those are all valid Lewis structures for thiocyanate ion. They all fit the octet rule. They all have the correct number of electrons. They all work. But they are also clearly different. So we can't say that the resonance hybrid is simply an average of all of those, because this isn't like nitrate ion. You can tell there's a sulfur on one side and nitrogen on the other side. Maybe there's a reason that like a nitrogen-carbon bond would be more stable than a sulfur-carbon triple bond or something, and so it like leans more toward one or the other. So these are non-equivalent resonance forms, and we can actually judge which ones are more likely to be more likely to contribute to the overall structure. Is the overall structure going to look more like one of them than the others, or is it going to be more of an average? So we need some criteria to evaluate that. And one criteria that we use is called formal charge. Formal charge is a way of describing where the electrons are and how happy everybody is with that. How stable the atoms are with more or fewer electrons. Remember how we put all the electrons into a big pot when we first start making the Lewis structures and then we distribute them? Formal charge kind of tells us, okay, how do we do on our distributions? Where's the most electron density? Where's the least electron density? And it works like this. You look at each atom in a structure, and you calculate the formal charge by taking the number of valence electrons of that atom. And this is the number of valence electrons in the free atom, not in the bonded atom. And then you subtract the number of bonds. And then you subtract the number of non-bonding electrons. Not pairs, but actual individual electrons. So let's try it. Let's take that first structure, SCN with the double bonds. Okay, so if we look at sulfur here, to calculate the formal charge, we take the number of valence electrons in the free atom. So what's valence electrons in sulfur? 6. And then how many bonds are connected to it here? And then how many non-bonding electrons? 4. You see the 4? So its formal charge is 0. Okay, then we do the same thing for carbon. Carbon has 4 valence electrons. There are 4 bonds connected to it, and 0 pairs of electrons. So its formal charge is also 0. And then for nitrogen, the formal charge is going to be 5 valence electrons minus 2 bonds minus 4 non-bonding electrons is -1. So when we draw Lewis structures, any non-zero formal charges that come up, we need to pay attention to. One thing is that the formal charges all have to add up to the overall charge of the ion. So this is a -1 ion, which means all of the formal charges have to add up to -1. Another issue is that non-zero formal charges are kind of saying that there's too much or too little electron density around an atom. So the ideal is to always have 0 formal charges on all your atoms. And so when we are judging Lewis structures, like is this Lewis structure good or not, rather than just following the rules of like the Octet rule, you also want to look at all the formal charges and make sure that they are 0 or as close to 0 as they can be. If you're getting formal charges above ±1, chances are that that is not a great structure, that it is not terribly stable. If you're getting a structure, if you have a choice between a couple of possible structures, and you have one where the formal charges are all 0, and you have one where the formal charges, there's like a +1 over here and a -1 over here, the one where they're all 0 is the better structure. So we can use formal charges as a way to evaluate these structures. So let's compare that one to the next one over. So you do this. Evaluate the formal charges on this structure. Whoops. Wrong one. Okay, what kind of formal charges do you get in that one? get some formal charges? So this one how does this one compare in formal charges to the last one?
Way worse.
Worse, right? Meaning higher formal charges. What kind of formal charges are you getting?
Like 1, -2, 0.
Yeah, so this one, the sulfur is +1, this carbon is 0, and the nitrogen is -2 formal charge. For our purposes, it doesn't really matter, but if you go into organic chemistry, formal charges become extremely important in how you can predict the reactivity and what's really going on. And so you'll always list non-zero formal charges by writing them on the ions and then circling them to show that they're formal charges. So in this case, we can see that these formal charges are much higher, much greater in magnitude than the previous one. So if we were judging these two resonance forms, we would say that second resonance form is probably not a major contributor to the overall hybrid. It's probably not, the overall structure is probably not going to look much like a carbon-sulfur triple bond. And it's probably not going to look much like a carbon-nitrogen double bond, single bond. It's probably going to be more like a double bond or a triple bond to the nitrogen. Another general rule you can use here I forgot something. In general, negative formal charges are better stabilized on electronegative atoms. This actually breaks down a little bit in the example that we just had, so that's why we're not kind of going through it that way, but we'll do another example in a second. So if you have a formal charge on, let's say, nitrogen versus oxygen in a structure, which one's more electronegative?
We have a what charge?
Well, let's just start with one. Which atom is electronegative, more electronegative, oxygen or fluorine? Remember from Monday? Fluorine, yeah, electronegativity all trends toward fluorine. I said nitrogen before, didn't I? All right, we'll say oxygen and fluorine instead. So that means that fluorine is going to be more apt to stabilize a negative formal charge than oxygen. So if you had two different choices of where to put the formal charge based on your Lewis structures, you would assign the formal charge. You would want to use the structure where the more electronegative atom has the negative formal charge. Another thing that's sometimes helpful, larger atoms can better stabilize formal charges because the charge is distributed over a larger area. So an atom like sulfur is going to be a little bit more stable with a negative charge than something like nitrogen. So let's try an example where this does work out. It'll also help you practice your Lewis structures. Draw 3 resonance forms for nitrous oxide, N2O. Just as a hint, N2O is connected NNO, not NON. That's one of the exceptions to the always go with the more symmetric one. So draw 3 resonance forms for N2O. It's a neutral molecule. Assign formal charges and rank the 3 structures in order of most to least stable. All right, so I'm going to help you with this a little bit, but I want you to do the first part as a review from Monday. Draw Lewis structure of NNO, but not just a Lewis structure of NNO. Draw 3 different ones that all fit the octet rule, but that are all going to be different in terms of formal charges. So they're all NNO, and they all follow the octet rule, but you can still arrange the number of bonds in different ways. Usually we do.
Oh,
So this is a this is
okay.
one where that doesn't work. Another clue to that is we also said that the first atom is usually the central atom unless it's hydrogen. And so because it's N2O, if it were NON, it would probably be written ON2 instead of N2O. You're stuck now. All right, what'd you come up with? So let's do this. Come up and draw a structure somewhere. You can use the backboards too, if you don't want to come up here. Or you can draw it on the computer. Let's see if we can find those three structures. Whoever goes first gets to pick their structure first, because you got to draw one that someone else didn't draw. Thank you. There's some markers here.
Should I also write how I got the amount of electrons?
Yeah, write the formal charges on the structure. Just the result.
Okay.
Plus minus 0, whatever.
Was 16. So. Oh, you took my goddamn.
Glad you have the same one. Is that okay? Do you want to switch to another one? No, we'll do that all together. All right, so I'm going to write these up here just as you have. Thank you very much. All right, so nice job on these. All the structures look great. First thing, of course, to look for when you're drawing Lewis structures is just make sure you're following all the rules. Second row atoms always need to follow the octet rule, with a couple exceptions that we're going to talk about in a minute. So we need to have octets around all of our atoms, which we do here for these 3 examples. Then we can calculate the formal charges, which you've all done nicely. So once we look at the formal charges, what can we say, at least for sure, right off? What's the first thing you notice? Yeah, this one's probably the least stable, right? Because lots of formal charges. Lots of formal charges usually means less stable. So we're going to say that one's probably not a contributor to the overall structure, not much of one. It's a valid resonance structure, it's great, but it's probably not a major contributor to the overall structure. The other 2 are more reasonable. They each have a positive and a negative formal charge. Which one's better? Okay.
This one all the way to the right, because oxygen is slightly more electronegative than nitrogen, so it's more going to accept the negative charge.
Right, exactly. So in our choice here is, do we want to have that negative formal charge on nitrogen or oxygen? Oxygen's the more electronegative atom, so that's probably going to be the more stable resonance form. So that they're actually ranked in order as we drew them here. So you got least stable, medium stable, most stable. So the consequence for the overall structure of N2O then is that it will probably look mostly like the one on the right. Both of these will contribute to the overall structure. So it's not going to be purely a triple bond, an NN triple bond, NO single bond. It's going to be somewhere in between an NN triple bond and an NN double bond, an NO single bond and an NO double bond. And it's probably going to lean more toward that side because that's the more stable. So that's the bigger contributor to the overall average structure. You can think of it kind of like a weighted average. That if we're averaging up these different forms, this one's going to have a very, very, very small weight. This one more, and that one the greatest. All right, so questions about this? Formal charges can also be used in non-resonance situations when you are kind of worried about whether or not a structure is correct. So there was a question about NON. Well, how do you know this is NNO and not NON? Well, let's try it. What if we didn't know that? We're on an exam. We didn't know it, and we said, all right, well, I know things are supposed to be symmetric, so let's go NON and see what we can do. So this structure should have 5, 10, 16 total electrons. We've got 2 accounted for, or 4 accounted for. So then we can go 6, 8, 10, 12, 14, 16. Okay, that's not quite enough electrons. So we need to make a double bond. So let's say we come up with a nice symmetric structure like this. 16 electrons, everybody's got an octet, looks great. Well, here's the problem. If we start calculating formal charges, we've got minus, 2 plus, and minus. That's not great. We know we really don't like to have plus 2 formal charges. We can rearrange this and draw some resonance forms, but in every resonance form you try to draw, if you fulfill the octet rule, you're going to have an atom that has 2 plus or 2 minus formal charges. So if we draw the resonance form that's like a triple bond and then a single bond, then the oxygen's still going to have a 2 plus formal charge, but the nitrogen's going to have now a 2 minus formal charge. That's not great either.
Is N2O the only one that's going to look like that, or are there other ones that we're going to have to?
There's probably other ones, but this is a way to evaluate that then. Because when you draw these structures, you look at it and you go, wow, these formal charges are all terrible. They're all like plus 2, minus 2. I can't get any kind of reasonably neutral formal charges here. That should sound an alarm in your head that this structure is wrong. Something is wrong here. Maybe you miscounted the electrons. Maybe you didn't connect the atoms in the right way. Something is wrong. You can do the same thing in pretty much any situation. So even like in NO3 nitrate ion. We know what nitrate ion looks like now, but what if you didn't? And what if you tried to do something like that for nitrate ion? If you actually go through and try to make that structure and calculate formal charges, the formal charges will be all over the place. And that'll be a clue that's like, oh, this is not right. Something is not right here. So you can, whenever you draw, just to be clear, let's do this. Whenever you're drawing Lewis structures, calculate the formal charges on the atoms, draw them on there, and that'll be a good check as to whether things are correct or not. Again, this is something that takes practice. So the more you practice this, the more homework you can do, the more you can try this, the more you start to just recognize, oh, every time oxygen has 2 bonds and 2 lone pairs, it's got a formal charge of 0. Every time nitrogen has 3 bonds and a pair and 1 lone pair, its formal charge is 0. So you just start recognizing what the different situations are, and then it makes it even easier to know whether you've drawn something that makes sense and that's right or not. So it just takes practice in seeing a bunch of these in different ways. All right, before we get on to all the exceptions, let's talk about drawing Lewis structure for organic compounds. Organic chemistry used to be thought of as a totally separate domain that was completely that molecules that came from living things could never be the same as molecules that came from non-living things. Now we know that's not true. Molecules are molecules, but the name has stuck. And now organic chemistry is mostly talking about the chemistry of carbon-based compounds. Carbon-based compounds that usually also have hydrogen, oxygen, nitrogen, and maybe some other stuff, but mostly those. So the big trick, or not trick, but the big thing that's different about organic compounds is because they're bigger, when the formulas are written, they're usually written in a way that helps you to figure out how they're supposed to be connected so that you don't have these kinds of problems, like which thing comes first, which thing goes in the middle, which thing goes in the outside. So for example, there's an organic compound called nitromethane, and its formula would be written like this: CH3NO2. Now if you're just looking at all of that, you might have a quick bit of panic if that showed up on an exam or something, and you think like, oh man, that's a lot of stuff. Where do I put it all? How does it all connect to each other? So the nice thing about organic compounds is the formulas are usually written in the order where they're supposed to be connected, assuming you know a couple things. So one thing you should remember is, how many bonds does hydrogen make? How many bonds can hydrogen make? Just one. So hydrogen only has one valence electron, and it can only have in total 2 electrons in its valence shell, the 1s orbital. So we can only ever make one bond with hydrogen. So in an organic compound, usually the way they're drawn is the atom like carbon that makes up the major structure is written first, and then the things coming off of it are written second. So the 3 hydrogens being written right next to the carbon means 3H connected to the carbon before. So the subscripts are only used when the things in the subscripts are connected to the previous atom. So that actually holds for the nitrogen as well. That 2 means 2 oxygen atoms connected to this nitrogen. So we can now use that information to set up a kind of a shell for this structure where we know that there's going to be 3 hydrogens coming off the carbon. Then the nitrogen, and then 2 oxygens coming off of that. And the shape for now doesn't matter. We'll get into that in the next chapter. And then we can still finish our structure based on our technique. So we can total up the electrons, 4 from the carbon, 5 from the nitrogen, plus 3 is 12, and then plus 12 is 24.
For the organic compounds, can we say like the first element, like how we have the carbon nitrogen, those two are always going to be like the central atoms that are bonded together, and then whatever comes after them is connected to that?
Yeah, generally that's how it works. So we still got 24 electrons. We used up 2, 4, 6, 8, 10, 12. So we've got 12 more to get in there. So we can go 2, 4, 6, 8, 10, 12. That uses up all our electrons, but then what's the problem? Anybody see a problem?
Nitrogen only has 6.
Yeah, nitrogen doesn't have an octet, so how do we solve that? Right, we're going to take one of the pairs of electrons off, and instead turn it into a double bond. And then that's pretty much done. We can also notice a couple other things here. If you were to calculate the formal charges, you would find a negative formal charge on oxygen and a positive on nitrogen, and everything else would be 0. So that's reasonable. The other thing to notice here is that there's a resonance form. Does anybody see what the resonance form is? Right, you switch the double bond with the oxygens like this. And that will also switch the formal charges. So negative and positive. That's correct, because an H can only ever have 2 electrons in its valence shell.
That's the only one.
It's not. We'll talk about some other ones in a little bit.
Is shorthand for this, you just don't write the H's, because it's just, you just write, like the bond.
Kind of. You probably wouldn't really do that because it might be confusing in a structure this small. But for larger structures, sometimes, yeah. Yeah. There's another way of writing those. Okay, so you'll get to practice those. Even though it looks kind of new and different, in general, the organic structures are easier to draw the Lewis structures of, because the bonding behavior is very predictable. Carbon in a structure like this is always going to have 4 bonds. Nitrogen's always going to have 3 or 4. Oxygen will have 1 or 2. Hydrogen will always have 1. Like, everything is predictable. The inorganic structures, like the ones we're going to talk about next, you can have a lot more variety. So they end up, you have to construct them a little bit more carefully. As you practice these, I think you'll like the organic compounds. You'll find them a little bit easier to draw. All right, let's talk about the exceptions to the Octet rule. There are 2 classes of exceptions to the octet rule. One is the elements that can have less than an octet, and one is the elements that can have greater than an octet. So anything that has fewer than 4 valence electrons is an exception to the octet rule, because it just doesn't have enough electrons to make, it's an electron deficient thing, it doesn't have enough electrons in there. And then hydrogen doesn't quite fit in this category, but hydrogen just having a smaller valence shell won't have 8 electrons. Hydrogen has its own rule, which is sometimes called the Duet Rule, because it always needs 2 electrons. So hydrogen always needs 2, as does helium, although helium doesn't make compounds, so it's not really an issue. Lithium we don't really talk about in terms of Lewis structures, but beryllium generally can have less, can have 4. Again, that doesn't come up a lot. Boron, 6. So you can see, like, until we get up to carbon, we really have fewer electrons than we need to make a full structure where everything has an octet. So those things don't get octets, and they do some interesting things to accommodate that. We'll see some of those structures in a bit. They can have an octet, but that means that when you're drawing a structure like BF3, there's a couple ways you could draw it. If we draw it like this, all the formal charges are neutral, but boron doesn't have an octet. If we draw it like this, like this, well, now everything has an octet. But boron's formal charge is going to be -1, and fluorine's formal charge is +1. And the actual more correct structure for boron trifluoride is this here. And that's for a couple reasons. One, because fluorine is so electronegative, the idea of it having a positive formal charge and sort of giving some of its electrons to boron is not going to happen. You can actually couple BF3 with other species that will give it its electrons, but it's not going to actually form this resonance form. So this resonance form ends up being not much of a contributor to the overall structure. Boron would rather not have the octet in this case. Okay, and then the other side of the exceptions are the things that can have more than an octet. And this is everything the third row and below. All of the atoms in the third row and below, because of the d orbitals, can accommodate more than just 8 electrons in their valence shell. So that's everything from like sulfur to chlorine to, usually it's the nonmetals that we're dealing with this, because transition metals don't really, this Lewis model, the localized electron model, doesn't work well with transition metals. So we're mostly talking about the main group, nonmetals over here. But everything kind of that bottom three, from the third row down, can have more than an octet. So we often draw these Lewis structures with violating the octet rule, having more electrons around those species in return for having neutral formal charges. So let's look at an example there. Let's look at sulfate ion. Sulfate ion is SO4, 2 minus. And its electron count is 6 times 5 plus 2 for the 2 extra minus, which is 32. So there's 32 total electrons in this structure. So we could draw it like this. There's 8 electrons used. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32.
Why'd you do 6 times 5, not 6 times 4?
Isn't it 4 times?
Because sulfur is in the same column as oxygen. So sulfur's got 6, and each of the 4 oxygens have 6. So that's 30, yeah. All right, so that works from a first examination. We've got all the octet rules taken care of. We've used all our electrons. Everything looks great. However, anybody have an idea of how we might find a problem here? Yeah, our formal charges are going to be a little bit crazy. So we've got minus formal charges on all the oxygens. And then we're going to have a +2 formal charge on the sulfur. And those are all pretty high formal charges. So if we want to minimize the formal charges, what can we do?
Change number of bonds.
Yeah, and how do we do that without changing the number of electrons?
You move 2 oxygen to a like between, so.
Right, so we would shift some of those lone pairs into bonds. And it doesn't matter which ones you pick. And if we do that and recalculate our formal charges, well, now we have still two 1 minus formal charges. But that's okay because we have to, because it's a 2 minus ion overall. So we're going to have some formal charges because the formal charges all have to add up to the overall charge of the ion. So in both these cases, we have an overall -2 charge, which we would expect. But the second structure minimizes the formal charges. Sorry, some water. All right, so some people, we should also say that some people would have a problem with that second one, even though that's the way the book would say to do it. It is true that it's a little bit questionable to say that sulfur and oxygen double bond because of stuff we'll get into in the next chapter about what it really means for something to double bond. So this structure, some people would say this is actually the more correct structure based on the experimental evidence. However, so the criteria needs to be clear. In this case, what we're doing and what the book always wants you to do when you work through your homework, what the exam is going to want you to do, is to draw structures that minimize the formal charges. And the Lewis model, this localized electron model, has a lot of drawbacks. And this is one of them, that this may not really make a whole lot of sense from a true reflecting reality standpoint. But it's still useful to be able to draw that in that way and to minimize the formal charges. All right, let's try some on your own. Yeah.
So the sulfur can have 6 bonds on it because it's in the 3rd row.
Right. So it's in the 3rd row. So now we don't care so much that sulfur has an octet, whether or not sulfur has an octet, because it technically now has 12 electrons around it.
If you double bonded everything, would you come to the same conclusion?
Sort of. So you could try it. Anybody know what you would get if you double bonded everything? Yeah, you'd get a -2 on the sulfur. So you'd end up, Yeah, so this way the oxygen is better stabilized with the negative formal charges, and that's why we leave it like that. If you added any more bonds, you'd start shifting the negative charge to the sulfur. Yeah, good question. All right, let's try some. So I'm going to list some molecules and ions, and I want you to draw the best Lewis structure you can, meaning everything correct, following all the rules, minimizing the formal charges. All right, so here's 5 for you to try. So if you have some structures and you're feeling however you're feeling about them, you don't have to feel great about them, but if you wouldn't mind drawing them on the board, but on the back or side ones, so that everybody who's still working can ignore them until they're ready. But just if each person can maybe just draw one for now, even if you think you're wrong, I would like to see what different people have drawn, and so we can think about how to critique these structures and how to tell which ones are working and which ones are not. You get a couple more? Couple more structures. Then we can talk about them. got 3. Only 2 more to go. Got 13 people here. So we want to draw a couple. Remember, they don't have to be right. I don't even know who drew those. It's totally anonymous. I just want to see some structures. Wouldn't you rather have your structures corrected today than on the exam next week?
I know my
What?
like the third one, the second one, sorry. So it's like xenons in the middle.
Yeah, so put up what you've got so far, if you don't mind, so we can see it. That's fine. That can be really helpful.
So you can put the little nub dots on O when it's in the middle, and you can't do that with a normal.
What? What do you mean?
The little nubs on the top.
The lone pairs, the non-bonding electrons?
Yeah.
Well, you can put them on any atom that needs them.
So for the xenon F2 one,
Mm-hmm.
you said anything lower than the third row can contain more than 8 electrons, correct?
Right.
So is that like on the right track for that one?
Yeah, so you're going to have to need that for that.
Ridiculous numbers if you only do
Right.
these for xenon.
Right.
So would you do like triple bonds and then 3 electrons on the
Yeah.
fluorine? Okay.
Well, no. You would just add a bunch more electrons to the xenon.
Okay, I guess I haven't calculated the
We'll go through them when we look at them here, so then you'll be able to see. Alright, let's take a look at some of these just because we're running out of time. So they look nice. Structures, everybody. Does anybody, looking at these, does anybody see any issues or potential issues that we should look at? What do you see? The CO here? Yeah, so the overall sum of all the formal charges has to be the same as whatever the overall charge of the molecule is. So in this case, CO is a neutral molecule. So that means if something's off, if we've got a -2 formal charge and a 0 formal charge. So let's check some different stuff. First thing to check is just the electrons. So 4 from carbon, 6 from oxygen, there should be 10 electrons. 2, 4, 6, 8, 10, 12. So there's our issue, is we've got too many electrons here. That's what's causing that problem. So let's fix it. All the atoms do have an octet, by the way, that part's fine. But we only have 10 valence electrons to work with, and there's 12 shown in this molecule. So that's not going to work. So let's take 2 away. So what happens now? What's the problem now? Yeah, now carbon doesn't have an octet anymore. So how do we fix that? Right. And we can't just add the bond, because that would be adding electrons, right? We have to take away some of these and turn them into a bond. Now we go back and look at our formal charges, and you'll find that oxygen has a positive formal charge, and carbon has a negative formal charge. And that certainly looks weird, and that looks like, I don't know, but it's really the only possibility here. Because carbon and oxygen both have to follow the octet rule, there's really nothing else we can do to make that work. And that is indeed the structure of carbon and oxygen. You can't have 4 bonds. You can never add a 4th bond. All right. Anybody else see issues with any of these? Yeah.
I think the xenon one has enough electrons.
Okay, let's count it out and see. So this one doesn't show the formal charges, so we can't tell yet. That's okay. Let's count up the electrons and see. So xenon would be 8. Fluorine would be 7. So that's 7 plus 7 plus 8 is 22. 2 2, 4, 6, 8, 10, 12, 14, 16. Yes, we don't have enough. We need 22 electrons. We also know that because fluorine's so electronegative, it generally doesn't make multiple bonds very well, like when we talked about with boron. So let's go back to our single bonds and see if we can deal with this without having to put double bonds on fluorine. Sometimes you do, but sometimes you can make it work without. So especially since we know we have a lot of electrons to use, we may not really need multiple bonds because we got so many electrons there, we can just put them everywhere. How many electrons did I say? 22. All right, so 2, 4, 6, 8, 10. Let's go 12, 14, 16, 18, 20, 22. If we look at our formal charges now, they're actually all 0. So that's a pretty good structure. This xenon in the middle has a buttload of electrons, 2, 4, 6, 8, 10, but that's okay because it's below the 3rd row. And the formal charges are all non-zero. So that's probably the best structure for this one. These are weird structures, by the way. You know, we call them the noble gases because they're not supposed to make compounds. And of course, because people like to play with stuff like that, they're under pretty extreme conditions, you can make compounds of xenon and fluorine. Fluorine being the most electronegative non-metal. So these are not like common compounds, but they're often used in these types of exercises with Lewis structures because how else are you going to get these kind of weird species with 8 valence electron, or with 8 valence electrons. All right. So this organic one looks good. I would lose the brackets just because it's not charged. The brackets usually mean that we're dealing with an ion of some sort, but the structure itself looks good. This one over here, perchlorate ion. I would make this a little bit different. Any idea?
Move on to one of the oxygens, so that's so oxygen would make it instead of fluorine?
Yeah, oxygen's going to be a little bit better with a negative charge than chlorine. That's not something that you might have been able to see without me telling you that because they are hard to judge. But chlorine is a little bit less. So this structure is better if you leave the neutral, let the chlorine be neutral, and put the formal charge, the negative formal charge on one of the oxygens. And then there are 4 different resonance forms you could have with this one too. So that's another reason for that. If we drew the 4 different resonance forms of the perchlorate ion, each resonance form would have the negative charge in a different oxygen. So another way we can say that is that the the negative charge is delocalized or shared around 4 different oxygens, which helps stabilize it. Because each oxygen in the structure really only has a quarter of a negative charge if we think about the hybrid. If we put the negative charge on the chlorine, then we're saying the negative charge is stuck on the chlorine. So it's better if we can share that, pass that negative charge around all the oxygens. And that's why this structure is supposed to be. All right, I think that's all 5. Sound good? Okay. Thank you for drawing those structures. Those of you who do structures. All right, the last thing we're going to talk about in Chapter 9 is bond length and bond strength. Almost out of pages here. Bond energy is defined as the amount of energy it takes to break a bond. So that is usually a positive number. So like if we wanted to know the bond energy of a chlorine-chlorine bond, you would take some chlorine gas, Cl2, and you would use a bunch of energy to break it into individual chlorine atoms in the gas state and measure the amount of energy that you had to put in to do that. In this case, 243 kilojoules per mole. So that's how much energy you have to you use to break that. So that number by itself is whatever, but what becomes interesting is when we compare it to other bonds, and you can get a sense of what types of bonds are stronger than others. So there's a table in your book. Here.
Where did that come from? 243?
What do you mean? From experiment. So you do it, you break the bond, and you measure how much energy.
Is there, is somebody gonna tell us that, or we just?
Yes, I looked it up on the table. Yeah, I'm going to get the table right now and put it in there. So here's a table of some bond energies. You can find it in your book, or you can find it here in the notes, since I just put it in there. All right, and you can see, like, relatively speaking, there's a pretty big range. Some of the strongest bonds are, of course, the multiple bonds. So multiple bonds tend to be stronger than single bonds, but not in a linear fashion. In other words, like, here's our carbon-carbon bond with its bond energy. The double bond is not double, but a little less than that. And then the triple is a little less than another one. But the triple bond is the strongest with the most energy, and then double, and then single. That's true across the board for any types. Some other trends you might find is that, well, the hydrogen-hydrogen bond is extremely strong. That's one reason that hydrogen is being looked at as a potential fuel, because one of the reasons that hydrocarbons or fossil fuels work so well as fuels is they are made of carbon-carbon bonds and carbon-hydrogen bonds, which is way up at the top, some of the highest bond energies. So other types of fuels don't have as much energy in them, and that's why it's been really difficult to replace those. You got a lot of energy in a pretty small package with those types of bonds. You don't have to know any of these numbers, but one thing you're going to be asked to do in the homework is to calculate some overall energies of compounds. So what you can do is, if you just add up all the bonds, all the energies on each side of an equation, and then you subtract them, you can find the overall amount of energy that changed in that equation. And it's literally you just add up the bonds and subtract them. So you'll get a chance to play with that a little bit in your homework. Another interesting way that we can talk about that is bond length. Now, bond length sort of tracks with bond strength, but not exactly. So you'll notice, like, in the same realm, you can make some pretty good rules, like triple bonds are always shorter than double bonds, which are always shorter than single bonds between the same two atoms. If you look at that table, you'll see that that is indeed true. A carbon-carbon triple bond is shorter than a double bond, which is shorter than a single bond. A nitrogen-nitrogen triple bond is shorter than a double bond, which is shorter than a single bond. Comparing bond lengths between different types of atoms is really hard, because it's not just about the bond strength, it's also about the size of the atoms, the types of orbitals that are interacting. So to say, like, that you can predict that, I don't know, a carbon-hydrogen bond is going to be longer, or let's say longer than a fluorine-hydrogen bond, you can kind of predict that because you know fluorine is smaller, but sometimes those are hard to say. So what you need to know about bond lengths is, I would say most importantly, the multiple bond effect. The fact that double and triple bonds are going to be shorter than single bonds. And then also, what's maybe more a little bit common sense, that smaller atoms will generally have smaller bond lengths. So if we compare, like, the halogens, FF, ClCl, Br, Br, and II, you can see that as you get bigger atoms, the bond length increases, which makes sense because the atoms are bigger, they're going to have to be a little bit farther apart when they connect. All right, so putting those together, bond length and bond strength sometimes go together, but sometimes don't. So it's really hard to predict that. sometimes. In a situation like this, it's very clear, works exactly as you'd expect. Triple bond is going to be stronger than a double bond, stronger than a single bond. Also shorter than a double bond, shorter than a single bond. The stronger the bond is, the shorter it is. But that doesn't always work. So if you look at this one, the bond length is dictated by the size of the atom. So fluorine's the smallest, then chlorine, then bromine, then iodine. That part works. But the bond strengths kind of bounce around. The strongest bond is the NF bond. The weakest bond is the Ni bond, but the other two aren't in order in the middle. And that has to do with these kind of compounding factors of both size and also the types of orbitals that are involved in these interactions. And in chapter 10, we're going to look at specifically what orbitals are involved when we say a bond. What type, where are the electrons, and how do these things connect together? So you think you can do this?
So can you explain the whole like equation thing? Like what does that mean? Cl2 gas, and then you go to Cl. Like,
Yeah, that means that.
so would a question be asked about that? Yeah, that what would you ask about that?
Like what's the energy of a chlorine bond? So that's where that energy comes from.
So it'd just be ClCl?
Yeah.
Okay.
Because you've got a chlorine molecule, that compound breaks apart, takes a certain amount of energy to break it apart. That's the amount of energy that it takes to break it apart.
So in the homework, there's one that's CH3CH2OH.
Okay.
How do you find that?
Okay, good question. So
H3.
here, I'll leave this up on the screen. And let's put it up on the board here. All right, so say that again, CH3.
CH2OH.
So we want to know the total energy of this compound as calculated by the bond energies. Well, in order to do that, you can't necessarily tell just from looking at this formula. We need a Lewis structure. Because if we have a Lewis structure, we'll know exactly how many of each type of bond there is. So we draw out the Lewis structure. In this case, it's going to look like this, because we know hydrogen only has one bond. All right, so we can draw a Lewis structure and we get this. And then we can account for all the different types of bonds here. So in this structure, I see 1, 2, 3, 4, 5 carbon-hydrogen bonds. Okay. I see 1 carbon-carbon bond. I see 1 carbon-oxygen bond. And I see 1 oxygen-hydrogen bond. 1, 2, 3, 4, 5, 6, 7, 8. 5 plus 3 is 8. So that's all my bonds. So then I would look up each of these bond energies in the table. These are 414, 347, 360. What is that one? 464. So this one has to be multiplied by 5. And then added to all the other ones, and that should be the total energy.
And so then for the next part of it is O2, would you again draw the Lewis structure to figure out if it's a single or a double bond?
Right.
And then there's 3 of them, so you multiply it by 3 once you figure
Yes.
that out.
Yep. So for an entire equation, you need all the Lewis structures of everything in the equation. Then you add up all the bonds on one side and all the bonds on the other side, and then subtract them. Yeah, it's a lot of work, but the more you do it, the more, once you get comfortable with this, you may not even need to draw this Lewis structure to be able to pull this out of this once you've done it a few times. Yeah, practice up with that. So tomorrow in lab, we'll be doing the copper spectroscopy. You don't need to prepare pre-lab other than preparing your notebook for it. And if there is some extra time at the end, it would be good to work a little bit on practicing this stuff because, again, I want you to look at chapter 10 this weekend. Make sure you get a good head start on it because we'll talk about it Monday, but then there's only 2 days until the exam. So you really want to get going on that chapter 10 homework before Monday.
The lab isn't posted
Oh, okay, I'll turn it on right now. I must have left it up. For the other one? There's no separate post-lab assignment. The questions were all in the lab yesterday. Like the
6 questions.
the 6 questions or whatever that were at the end of the lab yesterday. That's what the post-lab is.